Welcome to this explainer. I am absolutely thrilled you're here. Look, if you're a student in the medical sciences, you know exactly how it feels to stare at an ECG for the very first time. It just looks like a chaotic, intimidating mess of squiggly lines, right? Well, today we're going to change that. We're going to treat the electrocardiogram not as some unsolvable mystery, but as a piece of architecture. By the time we're done here, you'll see these waveforms and intervals as perfectly logical building blocks that tell the precise story of the heart's electrical cycle. I mean, think about it for a second. How exactly do you translate a three-dimensional beating muscle into a two-dimensional series of lines on a page? That is the fundamental challenge of electrophysiology. And as students and future clinicians, mastering this translation isn't just about, passing a test. It is quite literally the skill you'll use to recognize when a patient's heart is crying out for help. So we're taking these theoretical concepts and grounding them right into the physical reality of the patient lying in front of you. Okay, let's dive into this. Here's the architectural blueprint we're going to build together today to completely lower your cognitive load. First, decoding the ECG grid. Second, the primary waveforms. Third, timing the key intervals. Fourth, the cellular connection. And finally, spotting clinical abnormalities. All right, part one, decoding the ECG grid, the foundation of the blueprint. To build our structure, we obviously need to lay down a solid foundation first. Before we can even look at a single waveform, we've got to establish the basic ground rules of the grid paper itself. It's basically the canvas for our blueprint. Now, the first rule of the grid is time. On an ECG, time always runs horizontally, from left to right. Look at the absolute smallest box on that grid. That single, tiny, millimeter-wide box represents exactly 0.04 seconds. Everything we measure regarding how long it takes an electrical impulse to move through the heart relies entirely on counting those little 0.04-second increments. The second rule of our grid is voltage, and that runs vertically. We measure the electrical amplitude or the sheer power of the heart's signals by looking at how high or deep those lines go. The standard calibration is that 1 millivolt of electrical energy equals a 10 millimeter high structural peak on the paper. So, horizontal is time, vertical is voltage. Boom. Now we have our foundation. Let's move to part two, the primary waveforms, building the structures. Let's see how our foundation builds into the actual physical structures of the heartbeat. We're going to construct the primary ECG waveforms, which, by the way, are just labeled alphabetically to represent specific phases of cardiac activity. But before we get to the specific waves, I want to give you a really solid mental anchor. Every single wave you see represents one of two things: depolarization or repolarization. Depolarization is the active firing. It's that rapid upstroke of electrical energy sweeping through the heart muscle, basically shouting at it to contract. Repolarization, on the other hand, is the recovery phase. It's the electrical reset that prepares the heart for the next beat. Keep those two concepts firmly in your mind. The heart's electrical cycle unfolds on paper in three main chronological steps, right in order. We start with a P wave, we move to the massive QRS complex, and we finish up with the STTU complex. Let's break each of these down. Step one is the P wave. This small initial bump represents atrial depolarization. That's the upper chambers of the heart firing. Now, a normal sinus-generated P wave has a very specific orientation. It should be upright or positive in lead 2 and negative in lead AVR. As a student, you should always check the P wave shape. If you see a peaked P wave, that's a massive red flag for right atrial overload. If it's notched, well, you're likely looking at left atrial overload. The architecture is literally telling you the story. Next up is the QRS complex. This is the main event, folks, ventricular depolarization. It's huge because the ventricles are the powerful pumping chambers of the heart, and it actually happens in two major phases. First, the initial depolarization of the interventricular septum, followed immediately by the simultaneous firing of both massive ventricles. Because this happens so incredibly fast in a healthy heart, a normal QRS complex lasts only 100 to 110 milliseconds or less. It's just a quick, lightning-fast, powerful spike. Finally, we have the recovery structure, the STTU complex, which represents ventricular repolarization. It kicks off with the ST segment. This starts at the end of the QRS, a spot we call the J point, and stretches right to the start of the T wave. Now, this ST segment should be perfectly flat, just a quiet isoelectric plateau. After that comes the T wave, which is the active repolarization phase, and it typically points in the exact same direction or concordant with the main QRS vector. Sometimes you might even spot a tiny U wave right after the T wave. Keep an eye out for those prominent U waves because they often signal conditions like hypokalemia or low potassium. Part 3. Timing the key intervals. The hallways between. So, we've built the rooms of our structure, the waves. Now we need to measure the hallways connecting them. Now, what's really interesting about this is the sheer contrast in timing. We measure the PR interval from the beginning of the P wave to the beginning of the QRS. This represents the time it takes for the electrical impulse to travel from the atria, pause at the AV junction, and finally enter the ventricles. Normally, this takes about 120 to 200 milliseconds. Compare that relatively long AV junction travel time to the normal QRS duration of 100 to 110 milliseconds or less. The heart deliberately pauses, it waits, to let the ventricles completely fill with blood before triggering that lightning-fast ventricular firing. There are a couple of other key measurements you absolutely need to know. The QT interval measures from the start of the QRS to the end of the T wave. It's the entire duration of ventricular depolarization and repolarization. But because this interval naturally shrinks when the heart beats faster, we have to calculate the QTC. That's just the QT interval corrected for heart rate. Lastly, we have the RR interval, which is the time between consecutive QRS complexes, and that's exactly what we use to calculate the patient's instantaneous heart rate. Moving on to Part 4, the cellular connection, behind the drywall. So far, we've only looked at this surface architecture, but what's actually going on behind the drywall? And this brilliantly illustrates the connection. Notice how exactly the paper markings map to the cellular phases. The QRS complex we see on the surface corresponds directly to phase 0 of the intracellular action potential. That's the rapid upstroke of cellular sodium rushing in. That flat ST segment, that's phase 2, the plateau phase where calcium balances out potassium inside the cell. And the T wave maps perfectly to phase 3, the active repolarization, where the cell completely resets itself. So the ECG isn't just a drawing, it's a real-time monitor of cellular biology. Part 5, spotting clinical abnormalities. When the structure fails. As a clinician, your main job is to recognize when this beautiful architecture collapses. We're getting into the high-stakes clinical applications now to see what happens when the structure actually fails. Remember how we said a normal QRS is a quick, sharp 100 to 110 milliseconds? Well, the crucial point is that if you measure a QRS duration of 120 milliseconds or greater, you are looking at a major structural warning sign. This significant conduction delay indicates a complete bundle branch block. Basically, either the right or left bundle is failing to conduct properly, which forces the electricity to travel super slowly, cell by cell through the ventricular muscle. Even more critical, though, are the signs of ischemia and infarction, heart attacks. When the heart muscle is starving for oxygen, the entire architecture warps. You're going to see deviations in the ST segment, either ominous elevations or depressions. You'll see changes in T-wave morphology, like deep T-wave inversions, or those absolutely terrifying early warning signs we call hyperacute tall T-waves. Recognizing these structural deviations immediately is literally the difference between a patient going home and a patient being rushed to the cath lab for emergency intervention. But it's not just blockages that alter the blueprint. Metabolic states and drugs can totally warp the waveforms too. Notice how specific imbalances warp these intervals. Hyperkalemia, which is dangerously high potassium, physically pulls the T waves up into these tall, peaked structures and widens out the QRS. Conditions like hypocalcemia or even drugs like amiodarone will stretch out the QT interval, which creates a prolonged vulnerability during the heart's reset phase. Conversely, hypercalcemia or digitalis toxicity can actually shorten that QT interval. Finally, let's look at the overall height of the structure, the voltage. If the QRS voltage is low, measuring 5 millimeters or less in the limb leads, it means something is dampening the signal. This could be fluid around the heart, like a pericardial effusion, or extra air in the lungs from emphysema, literally blocking the electricity from reaching the surface electrodes. On the flip side, high voltage usually indicates ventricular hypertrophy, a thickened, enlarged heart muscle that is generating massive amounts of electrical amplitude. So, we've built the foundation, constructed the waves, timed the hallways, and learned exactly what it looks like when the walls start to crack. You are no longer just looking at random squiggly lines. The architecture is right there in front of you. You have the blueprint. So the only question left is, what will your next patient's ECG reveal? Keep studying, keep looking at those 12 leads, and thank you so much for joining me for this explainer.